Lesson 21 is about similarity, which in a previous lesson we talked about dilations, which are a type of transformation that change the size of an object without actually changing the shape. So that's where the word similarity comes in, because we need a word to describe objects that have the same general shape but not the same size. If they were the same exact size and shape, then we could call them congruent, but this is for the cases where you have two objects, same shape but different sizes. So starting from the top, dilations result in figures that are the same shape but not the same size. Because figures in a dilation do not have the same size, we cannot say they're congruent. Figures that have the same shape but not necessarily the same size are similar. So same shape, like a square and a square, but one is bigger than the other, they're still similar. So similar figures have congruent corresponding angles and then proportional corresponding sides. So in our similar figures here, D corresponds with N, and those are both right angles. C corresponds with M, those are both right angles. So far we have two pairs that are congruent. A corresponds with K, those are congruent because they have the angle with the one tick mark. And then B and L are corresponding and congruent because they have the angle with the two tick marks. So far, all of the corresponding angles have been congruent. So that kind of checks the first thing that must be true in order for figures to be similar. The second thing is that corresponding sides must be proportional. So in this figure, AB corresponds with KL. And 1.6 is exactly half of 3.2. And then AD corresponds with KN, and 2.5 is half of 5. DC corresponds with NM, 1.5 is half of 3. And then BC corresponds with LM, and 2 is half of 4. So each of the red sides are just exactly half of what the blue side lengths are. Okay, so it checks both the boxes. They have corresponding angles that are congruent and then proportional corresponding sides. And then if we look at the two figures that are not similar on the far right side, just looking at say angle A and angle E, those are corresponding and they're not congruent. So as soon as you have one pair of corresponding angles that are not congruent, that would mean that they're no longer similar. They can't possibly be the same exact shape if the angle measurements are different. Okay, so moving down right here, it says in math, the symbol, and it's a little kind of curly dash, that means is similar to. So instead of writing out is similar to, we use that little kind of curly dash. It's similar to the congruent symbol, but it's just that one. And then if we have kind of that curly dash, the line through it means is not similar to if you have a equal sign and you put a line through it, that means it's not equal to. So just a new symbol, if you haven't seen it before, I would definitely write it down and have it somewhere handy so you remember what it means. And then moving down here, the following transformations can be used to prove similarity. So translations, reflections, and rotations, and then also dilations. The first three, those can also be used to prove congruence because those are rigid. Dilations can't be used to prove congruence though, because congruence means the same size. Dilation will change the size. So all four of these can prove similarity. Only the first three can prove congruence. But because basically if we can prove congruence, that also kind of proves similarity, because it's kind of every single congruent object is also similar because they're the same size. Congruence is just more specific. That's why those three can show both. So for this example, we're going to determine whether or not these two triangles are similar by finding the ratio between their side lengths. So ratios are just relationships between numbers, so 1 to 2 or 3 to 4, and you can write them with a colon or a fraction. There's several different ways to write them. For this problem, we're going to use this kind of formula over here where it says use the side length of the image over the side length of the pre-image for the ratio. You don't always necessarily need to do image over pre-image. You can switch it around. You just have to be careful that you'll see for this problem, we're going to create 3 different ratios, one for each pair of corresponding sides. And the order needs to stay consistent. So we would need to stay image over pre-image throughout for all 3. As long as you're staying consistent for all three ratios within that problem, it really doesn't matter which way you structure it. Okay, so in this problem, the blue is the pre-image, and then the red is the image. So this would be an example of like a reduction, something that's shrinking in size. So before we can actually find the ratios, I just kind of want to pair up and set up like a little like kind of mini formula for this problem where we pair up the corresponding sides. So what I mean by that is like one side on the image is EF. So I'm going to say, okay, one ratio is going to be EF, and that's going to be over the side length of the pre-image, which the corresponding side on the pre-image is BC. So over BC. And then another side on the image is FD. And then a corresponding side on the pre-image is CA. And then the third side on the image is ED. And then the corresponding side on the pre-image is BA. And then in order for these two triangles to be similar, the ratio between all of their side lengths must be equal. So all of these values should be equal to each other once we actually put in the side lengths. So they should all be equal. If one is not equal, they're no longer similar. Okay, so now for the side lengths, EF is 3.8. And then BC is 15.2. And then for the next ratio, FD is 6.1. And then CA is 24.4. And then ED is 5.3. And then the corresponding side, BA, is 21.2. So now we'll just, these fractions don't really mean a whole lot to me right now because they all have weird different denominators. So we're just going to change them all into decimal form. So to do that, you take the numerator and you divide it by the denominator. So for the first one, we do 3.8 divided by 15.2, which is 0.25. And then 6.1 divided by 24.4 is 0.25. And then 5.3 divided by 21.2 is also 0.25. So since we got all three equal to each other, that means yes, the triangles are similar because the ratio of all of their sides were equal. So we could say yes, they're similar. Okay, if I get one that's different, they're no longer similar. These ones are good though. Okay, so moving down to 21.2, we're going to identify similarity using transformations. So this is the only example from this section. So apply a series of transformations to map triangle ABC to triangle A prime, B prime, C prime. Okay, so clearly there needs to be some sort of rotation because the triangle is not really oriented in the same way. So it looks like if we're starting with the pre-image, which same thing, that's the one in blue. So we're starting with A, B, C, and we want to get to the image. It's the one in red, A prime, B prime, C prime. We definitely got to rotate it. The smallest amount of rotation would look like a 90-degree rotation clockwise. Yeah, so remember clockwise is this is clockwise, and then the other way is counterclockwise. So clockwise is CW, and then counterclockwise CCW, just as a little reminder, because you'll kind of see it throughout this section. So if I rotate something clockwise, for example, if I take the point A and I rotate it 90 degrees counterclockwise around the origin, so around 0, 0, that point where A is going to go from -2, 1 to 1, 2. So when you have a like 90 degree or like a 270 degree rotation, usually so what happens is the X and Y switch, and then one of them is going to change signs. I think sometimes like the formulas make it a little bit harder than it needs to be. So if we're rotating 90 degrees clockwise, we're going to go into like the next quadrant. So this is technically the first quadrant and this is the second quadrant. We're going to go into the first quadrant. The X and Y coordinates switch. So this was a negative 2, 1, and then it's going to rotate into 1, 2. And then in this case, we're going from like the second quadrant to the first quadrant. The X coordinate is going to go from, it was originally negative, it's going to become positive. These, like the exact formulas were from maybe like unit 1 or unit 2, but I can grab the screenshot of those for you guys and post it with this to make it a little bit easier. But yeah, either way. Oops, sorry, I hit the back button accidentally. This new point is going to be our A prime, and that's at 1, 2. And then if we kind of follow that same pattern, this B was at negative 5, 4. So negative 5, 4. So the X and Y's are going to switch. So instead of negative 5, 4, it'd be 4, 5. So up here, right there for B, sorry, and this should be B double prime because they already have like the single primes up there. So it's going to be B double prime. And of course, like we're going to have to do more than one transformation here. We're just doing one part of this so far. And then the last point, C, this was at negative 2, 9. So the X and Y will switch, so it'll become 9, 2. So 9, 2 is right here, and that's going to be C double prime. And I'm just going to add those points in also. So this was, B double prime was 4, 5. And then C double prime was 9, 2. Okay, so X and Y coordinates are switching, and then the Y coordinate is changing from negative to positive. So negative 2, 1 to 1, 2, negative 5, 4 to 4, 5, and negative 2, 9 to 9, 2. So I'm going to connect these now, and then now we have like a similar object that, you know, it's definitely like kind of below where we need to be. But the main thing is that it's like half the size of it. So I'm going to go, or not half the size of it necessarily, but it's like a smaller triangle. So I'm going to go through and label each of the points of like what we're trying to get to. And that might help us kind of see, okay, what change needs to happen to actually get to that red triangle. So far we've done a reflection 90 degrees clockwise. And then for, let's see if I could, I'm just going to draw an arrow too. For A prime, that point is 2, 4. For B prime, that point is 8, 10. And then for C prime, it's 18, 4. Okay, so I'm going to go ahead and just kind of erase the original points that we wrote here because we don't really need them anymore and it's just kind of really cluttered. But now, so for example, we have our like rotated triangle, that's the green one. A double prime is 1, 2, A prime is 2, 4. So how am I getting from 1, 2 to 2, 4? And then like C double prime is 9, 2. And then C prime is 18, 4. B double prime is 4, 5. And then B prime is 8, 10. So there's a very specific thing happening to both the X and the Y coordinates. They're doubled. Like if I take 1, 2, and I multiply it by 2, I get 2, 4. Or if I take 4, 5 and multiply it by 2, like each the X and the Y, I get 8, 10. If I take 9, 2, and I multiply both by 2, I get 18, 4. So we're taking that like kind of rotated triangle and we're dilating it by a factor of 2, and then that's going to give us the triangle that we're going for. It's going to give us A prime, B prime, C prime. So we just have to list the second like transformation. We'll just say dilate by a factor of 2. And then that's it. So in this workbook section, there's one of those tools that kind of it gives you basically a problem like this where it gives you an original figure, a pre-image, and then an image, and asks you to kind of select what dilations would get you from one to the other, or what transformations in general. I highly recommend playing around with that because it's just like kind of the fastest way to practice these without actually having to like physically graph each step, because it does it for you automatically.